Let x be a random variable following the normal distribution with mean mu and variance sigma squared. Its probability density function is the bell curve, centered at mu, with spread determined by sigma. Notice in the figure, the bell is shifted to the right of the origin. The center of mass sits at mu, which we take here as a positive value, so the shift is visually clear. This is the whole point of mu. It is not tied to zero. It is wherever the distribution is located on the real line. This distribution appears throughout probability, statistics, and every quantitative science. We will prove two foundational properties rigorously. First, that the expected value of x equals mu, confirming that mu is truly the center of the distribution. Second, that the variance of x equals sigma squared, confirming that sigma squared is truly the spread. The key insight is a single change of variable. We set z equal to x minus mu divided by sigma. This shifts the center to 0 and rescales by sigma. Under this substitution, x equals sigma z plus mu, and dx equals sigma doesn't. Any integral over the general normal distribution transforms cleanly into an integral over the standard normal, which has mean 0 and variance 1. All the technical work then happens in that simpler, cleaner form. This substitution is the single most powerful tool in normal distribution calculations. For the expected value, we begin with the integral definition. E of x is the integral of x times the probability density function. We substitute z equals x minus mu divided by sigma. Since x equals sigma z plus mu, the integrand becomes sigma z plus mu times the standard normal density. This splits into two separate integrals. I1, weighted by sigma, contains z times the standard normal density. I2, weighted by mu, is the standard normal density itself. We evaluate each integral in turn. Look carefully at the integrand of I1, z times phi of z, where phi is the standard normal density. This function is odd. For every positive value of z, the function is positive, shown in blue. At the symmetric negative value, the function is exactly negative, shown in red. The blue and red areas are perfect mirror images. When integrated over the entire real line, they cancel exactly. I1 equals 0. By symmetry alone, no computation required. The second integral I2 is the standard normal density integrated over the entire real line. This is a fundamental axiom of probability. Every valid probability density function must integrate to exactly 1. The probability of all outcomes combined is always 1. The gold-shaded area fills the entire real line and equals exactly 1. Therefore, the expected value equals sigma times 0 plus mu times 1. That is mu. The first result is proved. E of x equals mu. Now for the variance. By definition, variance is the expected value of x minus mu, all squared. This is the integral of x minus mu squared times the probability density. Applying our standardization substitution, x minus mu equals sigma z, so x minus mu squared becomes sigma squared times z squared. The sigma squared factor pulls cleanly out of the integral. What remains is j, the integral of z squared times the standard normal density. So var of x equals sigma squared times j. We now need to evaluate j using integration by parts. To evaluate j, we apply integration by parts. The integral contains z squared times e to the minus z squared over 2. We split this as u equals z, and dv equals z times e to the minus z squared over 2. Doesn't differentiating u gives do equals doesn't. For v, we need the antiderivative of z times e to the minus z squared over 2. Notice, the derivative of negative e to the minus z squared over 2 is exactly z times e to the minus z squared over 2. So v equals negative e to the minus z squared over 2. The integration by parts formula then gives a boundary term evaluated at plus and minus infinity, plus the remaining integral of e to the minus z squared over 2.
This is the critical step, the one where most students make an error. The boundary term is z times e to the minus z squared over 2, evaluated at positive infinity and negative infinity. At first glance, z grows without bound. This seems dangerous. But look at the graph carefully. The exponential e to the minus z squared over 2 decays with z squared in the exponent. That is far faster than the linear growth of z. Watch. As z increases, the product rises briefly, reaches a peak, then falls relentlessly back towards zero. Exponential decay always dominates polynomial growth. At both positive and negative infinity, the boundary term is exactly zero. It vanishes completely. With the boundary term gone, the remaining integral is the integral of e to the minus z squared over 2 over the entire real line. This is the famous Gaussian integral, one of the most important integrals in all of mathematics. Its value is the square root of 2 pi. Dividing by the square root of 2 pi from the normalization constant gives j equals 1. And so, var of x equals sigma squared times j, which equals sigma squared times 1, which equals sigma squared. Both results are now fully and rigorously proved. E of x equals mu. Var of x equals sigma squared. These results reveal something profound about the normal family. Mu and sigma squared are not derived results or convenient labels. They are the defining parameters of the entire family of normal distributions. Every member of this family is completely and uniquely described by exactly two numbers: its mean, which locates the center, and its variance, which controls the spread. Watch as sigma changes. A small sigma concentrates probability tightly around mu, a tall, narrow bell. A large sigma spreads probability widely across the real line, a flat, broad bell. The family is infinite, but each member is pinned down by just one number for location and one for scale. What happens as sigma approaches zero?